Hello students. Today in this video we shall discuss about moving coil galvanometer. This is a very important instrument in physics. Let us see what is the principle. It says that when a current carrying loop is placed in uniform magnetic field, it experiences a torque. The key words in this statement are uniform magnetic field. It means we must have a region where the magnetic field applied is uniform. We take a current carrying loop. Now this loop can be of any shape. It can be a rectangular loop or a circular loop. This loop is made up of conducting wire and it carries current. When such a loop is placed in uniform magnetic field, we will see that the coil will turn, will show deflection because of the presence of torque. So the coil placed in such region experiences torque. The diagram of this moving coil galvanometer is shown here. This is the diagram taken from the NCERT textbook figure 4.24. The elements of moving coil galvanometer are seen here. It's a top view. You see the two blue colored objects marked N and S. These are the two concave shaped magnets which provides the uniform magnetic field. The important point here is that the shape of the magnets are not rectangular but concave. The reason is that this concave magnet provides us with radial magnetic field. Now what is the radial magnetic field? It is the magnetic field which is uniform and it acts along the radius of the circle. So you can see the black lines originating from these magnets. They are pointing towards one center. They do not meet at the center because there we have a soft iron core placed over which the coil is wound. Thus the field lines, they start from the magnet and they end on the core, soft iron core. This soft iron core will also get magnetized and will enhance the magnetic property of the region. The coil is suspended and it can be either suspended or pivoted. Here the pointer is shown, which is a straight line up, which is resting on a scale, and it is supported from below with the help of a spring. You can see the spiral spring in the diagram marked with SP. So when current flows through the coil, it experiences torque and the coil gets deflected by certain amount. When the coil deflects, the pointer attached to the coil also moves and marks it on the scale. This is how we are able to read the amount of current that is flowing through the galvanometer. Having seen this schematic diagram, now let us see the video of an original galvanometer.
There are two types of galvanometers. One is suspended type. This is a moving coil galvanometer, suspended type. You can see the coil at the center. It's a rectangular coil made up of copper wire with the two concave magnets and the soft iron core. It is suspended through a fiber. The another type is pivoted type, where the pointer is lying attached with a spring and you have the scale. The concave magnets and coil is there inside this. The pivoted type galvanometer is opened. You can see the scale. This is the pointer which is broken now. This is otherwise a long pointer which points on the scale. When we remove the scale, we can see the soft iron core inside. The soft iron core is the cylindrical metal body over which rectangular coil is there. These are the two concave shaped magnets which provides the radial magnetic field. The pointer is connected to the coil with the help of a small spring. Thus, this is the pivoted type galvanometer.
Now when we look at the theory, it says when the current I flows through the coil, it experiences a deflecting torque that is given by torque is equals to NIAB. We know the formula of torque is NIAB sine theta. So what has happened to theta? Theta is the angle between B and A, that is the magnetic field and area vector of the coil. Because we have made the radial magnetic field, the coil is always parallel to the component of B, that is magnetic field. Hence, theta will always be 90 degrees. And we know that sine 90 is 1. Thus, we have reduced the equation to torque is equals to NIAB. Here N stands for the number of turns in the coil, I is the current flowing through the coil, A is the area of the coil, and B is the strength of the magnetic field. This deflecting torque will give rise to a restoring torque. The restoring torque developed in the suspension fiber or the spring is such that K phi is equals to NIAB. Here K is a constant called as the spring constant. The deflecting torque we have seen is NIAB. The restoring torque is K phi. Thus, we equate the two and shifting the terms, we see that phi is given by NAB upon K into I. This equation tells us that the deflection produced in the galvanometer is proportional to the current flowing through it. Because the bracketed terms are all constant, we have fixed number of turns, area of the coil is fixed, magnetic field strength is constant, and K is the spring constant. Thus we see that phi is proportional to I. Whatever current is sent through the coil of the galvanometer, there will be an equivalent amount of deflection produced, that is phi, and this deflection we read from the scale when pointer moves on the scale. So this is how a moving coil galvanometer works and gives us the result. The scale is calibrated for the amount of current flowing through the coil. Thus, phi proportional to I gives us the value of current, and we are able to read the value of current using a galvanometer. So that's all for this video. Thank you so much. Happy learning.